Good evening.
Good evening. Okay, sir. Ma'am Vasanta, ma'am, you can
Sir.
go for introduction.
Okay, sir. Okay. Good evening, everyone. Welcome to the sixth session of day 3. It is my honor and privilege to invite our distinguished speaker, Dr. Ramalinga Swami, sir, to address the participants and share his invaluable knowledge. Over to you, sir. Thank you.
Yeah. Very good evening. Good evening to all. Let me share my screen. Yeah, good evening to all. Today I'm going to discuss about the unsupervised learning. Okay, the content, the majority of the content has been taken from the HNK Camber, the data mining book. So from there, I majority of the content has been taken, but in between I have added the few contents from the other sources. Okay? The majority of the content has been taken from the HNK Camber data mine. He's a professor at the University of the Illinois. Yes, so today I'm going to discuss about the unsupervised learning. So maybe yesterday I was mentioning about the supervised learning. In the supervised learning, I can say that there is a presence of the supervisor, means an instructor. So the role of the instructor is to correct your mistakes. So when there is an error and the supervisor is rectify this error, and the learning is takes place. That's how the supervised learning algorithm works. The role of the supervised learning, the supervisor in machine learning has been replaced by the decision variable, the outcome, like a class variable. Okay, so if we are talking about any data set, so usually the data set. So we have a set of features. We have a set of features, and followed by the class information, the class label, or I can say a decision, isn't it? So this, the decision variable, the outcome of the features, is a positive or negative, or yes or no, it's a benign, malignant. Okay, so these decision variables will act like a supervisor. This I mentioned about the help of an example. Suppose if this information is not there, this information is not there, means you have only a set of features. So when the class information is missing, and this is missing, so how can we analyze the data? Analyze the data for interesting patterns. Interesting pattern. Right. This is called unsupervised learning. Unsupervised. So when there is no class information, there is no supervisor. This is something like a self-study course. You are learning a course on your own. Okay. So when you have a course, a direct course, when there is a presence of the supervisor, with the help of the supervisor, you try to learn. But this is something like, if I take the analogy in our real time, so where you will learn on your own without depending on any supervisor. Okay, something like self-study courses, right? So these unsupervised learning, the problems which are in the domain of unsupervised learning are solved by a technique called clustering. So means now you have to analyze the data for interesting patterns by using this clustering technique. The aim of this clustering technique is to identify the uh, similar objects that are mentioned. What is the clustering analysis? What is called a cluster? A cluster is a collection of the data objects. Not, I cannot say it's a data objects, similar data objects. I cannot cluster one item with other item which are the similar. So I'm interested in a grouping of the objects, I guess the data samples, which are similar in nature. So those data sample I'm considering as a cluster, like a group. Like in a group, suppose if I'm roaming with a group of 5 members, so because the similarity, if you take in some sense, we have some common taste. So if suppose I'm making a group, a friendship with some fellows, so almost I can say that by nature, by what is the nature, if you know the nature of me, I can sense in which group I'm roaming. So we can easily sense that the mentality of the other group members too, because they are similar in nature. In some sense, they are similar in nature. Maybe it may not be in all the aspects they are similar, I cannot say. In some metric, with respect to some sense, they have some commonality in that. So that's why they are making a group. It happens, groups are formed like that. Same way, the same idea is applied when you have a data set without any class label. So it's like you don't have any other choice. So you have to group the objects based on the similarity. The question is, how do we find this similarity? But there are different similarity measures are there. You can say the Euclidean distance. Of course, the distance is a similarity measure. If I take any two data points in the n-dimensional space, if I take the distance between these two objects, if the distance is less, it means that they are very similar in nature. If the distance is high, means they are more dissimilar. Okay. Right. So that is how we can calculate the different grouping of the object. So what is the cluster analysis? So far we have seen the definition of the cluster. So what is meant by cluster analysis? The cluster analysis is analyzing the cluster which have been formed by the clustering algorithm. So how many clusters have been formed and what is the quality of those clusters is all talked about in the cluster analysis. Yes, it is unsupervised learning. There's no predefined classes there in this case because there is no class information, because this information is missing in our data set. Now, where we can use the clustering analysis, like in the unsupervised learning, where we can use it. The typical application falls into the two categories. One is the standalone tool. One is the standalone tool means you can use the clustering on the data set is unlabeled. I can say there is no label information is there. So there you can use this clustering algorithm for identify the clusters, to identify the groups. And you can use it as a pre-processing tool. You can use it as a pre-processing tool. Before you want to apply the clustering classification algorithm, which I mentioned earlier. So sometimes we can use it. Maybe I didn't discuss about the KNN classifier, but if you want to improve the performance of KNN classifier, and some research have become, so they pre-process the data by using clustering, and once they've done clustering, then they will apply the KNN algorithm for better performance. So it means that the clustering analysis is not only used for direct, we can also use it for it as a pre-processing tool for certain other applications like that. Okay. So if you look at about the typical application of the clustering algorithm, so if you're talking about biology, so where in case of the biology application, so if I'm toxin of the living thing, so whether I want to group the objects which are belongs to the which family it is and which kind of species it is, and we can group them into based on their category. And of course, we can use this clustering technique for the grouping of the documents which are similar in nature, like the document which are related to the sports, the documents which are related to the business, the documents which are related to the family, the documents which are entertainment. So based on that, if you are talking about typical application, is if you are in the newspaper, so there are different kind of uh, zones where we have a specific information is being provided. Okay, so we can classify. So where this information is falls into. So we can group the information. So based on the what type of document it is. So we can group the clusters. We can group the items, objects, like documents. And the land use. Okay, suppose if I'm by looking at I can say that the images which are taken by the satellite, the image which have been taken by the satellite from your ISRO, suppose the high spectral images or hyperspectral images. So there we can, based on this, so we can identify in the given image, we can identify the similar objects by using the similarities of the features similar between the feature similarity. We can identify group these similar objects where a particular land where the similar crop will grow, where the empty land is there. We can group all these the places in an image by which is taken by the satellite from this. Just upon you can say marketing, city planning, earthquake, and climate. Everywhere we can use this the clustering algorithm. So the whole idea of the clustering is just to group the similar objects, group the similar objects. Now, what other applications? If I am say here, these are direct application. They are direct application of the clustering algorithm, where you can use this science of field directly group the objects, and we can also use this clustering algorithm as a pre-processing tool for. I think this I already mentioned, K-nearest-neighbor algorithm, which is the clustering classification algorithm. So we can also use as a pre-processing tool. So we can use it as a classification algorithm where you want to optimize, improve the performance of the KNN classifier. So you can apply the clustering on your data set. Then you can, what I can say, then you can apply your KNN classifier. So you can use it in image compression applications. Okay, so you can use it in image compression, even the outlier detection. So I will show in the outlier detection how we can use it in the clustering algorithm in the case of a DB scan algorithm. Okay, that time I will discuss. The outlier is nothing but in a data sample which is significantly deviating from the other samples. Okay, means like odd man out. Suppose if I am saying a numbers 2, 4, 6, 8, if I give the 9 or 11, this is the odd man out too, because of 2, 4, 6 at a multiplication of 2, but this is not the even number, something like so. The number which is significantly different, these are even numbers, and this is the odd man out. Okay, this means any sample which is significantly deviating from the normal samples. It's called outlier. So what is the aim of this? How do you identify the clustering algorithm is good or bad? So what is the aim of this clustering algorithms? Is the aim of these clustering algorithms is to create what I can say that very compact clusters. When I'm talking about the samples inside the cluster, should be very tight, or I can say compact in nature. So when I'm comparing the samples between the samples, it means when I compare the two clusters, so this distance should be more, so that I can clearly distinguish how many clusters are there in my data. So what I mean that when I'm talking about any good clustering algorithm, the essence of this good clustering algorithm is to generate the more compact clusters, as well as when I compare the single cluster, they should be very compact in nature. But when I compare the any two clustering clusters in any two clusters, so they must be what I can say that should be well separated. So how we can measure this compactness and well separatedness of the clusters? is using the intra-class similarity and inter-class. So the intra-class similarity will talks about the how the samples within the clusters, and inter-class similarity will talks about the how the samples between the clusters. Okay, so this, if I know how to measure this, so then with the help of these two measures, we can identify a clustering algorithm is good or bad, means whether the clustering algorithm is generating the proper clusters. The quality of the clustering method or the algorithm depends on the similarity measure used by the method. So how do you measure two samples are similar or dissimilar? So what kind of metric you are going to use? So either Euclidean distance or Manhattan distance or cosine or like this, Jacob index. So many measures are there. And what kind of similarity measure you are using, so that has an impact on the quality of the clustering algorithm. And also its implementation, how you are implementing, and its ability to discover some of or all the hidden patterns. Okay? So of course, these two parameters is with respect to the algorithm, I can say, because the functionality of the algorithm, the idea behind how the algorithm is defining these clusters, so that also matters a lot. So what are the different kind of the similarity measures we can use? I mentioned that any distance function, usually we consider as a similarity measure. Usually consider as a good similarity measure. Right. Now, what are the different kind of clustering algorithms are there? What are the different kind of the clustering algorithms are there? Okay, with this knowledge, the aim of the clustering algorithm is to group the objects, and we can use this either directly when the data set is stable, there is no class information, we can use the clustering algorithm alone. And if the data set even is a labeled data, so for certain classification algorithms, we can use this clustering as a pre-processing tool, like ANN classifier, radial basis function classifier. So there I can use these kind of the techniques as a pre-processing tool to improve the performance of the respective algorithm. Okay? Yes. So with this knowledge, what are the different kind of clustering algorithms are there related? So if you're looking at the algorithm which are based on the partition, means every time you will partition the samples, the sample space data set, you can say, in some number of partitions, and then every time we will calculate the centroid, and this centroid will keep on moving. Then there is a change in the uh, objects, and then again there is a shift in the centroid. So like this, it's an iterative process. So until we will meet the certain criteria, then there is no change in the centroids, I guess something. So there is a partition-based approaches where we can create the clusters by you partitioning your input space. And whereas in the hierarchical based, so we can iteratively we can build the clusters by starting with the single sample, or we can starting with the whole data set and dividing it like that. So you can create any number of based on the certain criteria. So there are certain limitations in the partition-based approaches to overcome. By overcoming those things, the people have developed these hierarchical-based approaches. We will see what is certain advantage, pros and cons of these things, and I'm discussing in detail. And there is the clustering algorithms based on the density of the density of the samples which is there in a particular location, I can say. So based on that also we create the density located regions, and by connecting these density located regions, we can create the clusters. Okay. Then other sort of clustering algorithms is called the grid-based techniques, where we will divide our input space into the cells, and then again we can apply the density measure, and from that like that. Okay? So under every categories of, if we're talking about partition-based algorithm, the famous algorithms are K-means and K-medians algorithm. So in the case of hierarchical based, we have the algorithm for Diana and Agnes. So of course there are some other algorithm is also the Ditch and Chameleon and also, but we will rarely use this algorithm, but these are two famous. So in coming to this, the density-based approaches, we have a the famous algorithm called DB scan. Of course, optic is also famous. We'll see how it works and under the grid-based approach. If I'm using grid-based approaches, so we have a click and the sting algorithms are there which will perform this grid-based technique along with the density approaches to form the clusters. We will see in detail. Okay? So how the partition-based techniques works? In the partition-based techniques is the partition every time we will partition a database, means the partition of data set D into n objects, means the data set D has been divided into some number of portions logically. Basically, so this is called partitioning. Every time it will partition the same number of objects. Where how many partitions you have to split your data set, partition data is k number of partitions. Okay, into a set of k clusters. So every partition I am calling as a cluster, such that the sum of the square distance is. What is the criteria we are following? When I sum it up all the distances to this point, all this distance from inside this cluster to its centroid should be minimized. What it's giving actually, if I take any clusters in the partition, so every partition is nothing but a cluster. Okay, if there are points over here, and so this particular partition or cluster will have the centroid. The centroid. So I can this centroid I'm calling as a C of I. C of I. Right. What I'm trying to say that this yes, Khan, if you have any queries, please let me know. Somebody raise their hand. Okay, no queries. Yes, what I'm trying to do that here is so from the centroid, you are finding the distance between all the points, and so this P is the point. P is the point between these clusters. P belongs to the point in the cluster. From every point in the cluster to the centroid, you are finding the distance and you are squaring it. So of course, because Euclidean distance is a square root, when I square it, so these two will get cancelled. So we will have the actual term, x minus x or something. Right. Right. So what is this innermost summation will give the spread or standard deviation is the spread means the standard deviation of the data set. Basically, it gives the how your data has been spreaded. So this is the spread of your data. So compactness of a cluster. So how many clusters are there? There are k number of clusters. Hence, the outer summation is talking about the. So for k clusters, for every cluster, I am finding the spread. So this is I'm calling as error function, and this I want to. This I want to minimize. So what is mean by minimizing this error function? Means we are essentially building the compact clusters, isn't it? More compact clusters. So this was the idea of the partition algorithm is every time your data set is being partitioned into k portions, and portion it will identify the so for every cluster, for every partition, it will identify the centroid, and from the centroid, all the rest of the points, it will find the distance and square it to get the spread. And this spread we want to minimize. So this error I want to. That is how the partition based. So why it is iterative? Because every time the cluster initially the cluster centroids are initialized randomly. But over the period of time, this cluster centroid will keep on changing so that there is a movement in the objects. Hence, there is a result in the clusters. So once these cluster centroids are stabilized, means there is no change in this positions, it means that there is no mobilization of the objects here and there. Hence, we can terminate that. Right. But what is the drawback of this partition-based method? Given a k, time given a, how do you give this k value? What is this k value? That's the biggest challenge. The given a k, to find a partition of the k cluster that optimizes the chosen partition. Right. The question is, what is this k value? Let's say k is equal to 2 or 3 or 4 or 5 or 6. What is this value? So this is the biggest problem in the partition based method. Right. Now, the technique which follows is called k-means algorithm and k-means algorithm. K-means and k-means. Of course, there are little variation in the k-means and k-means. So, first let us see how the k-means algorithm works. And this k-means algorithm has been proposed by the McQueen and Lloyd in the year 1982. Okay, and what is the idea of this k-means algorithm is that each cluster is represented by a center of the cluster. However, the cluster is being represented, the center of the cluster is being nominated or represented as the center of the cluster, represented by the cluster. The cluster is being represented by the centroid. Okay, that's. But in the k-medides, is each cluster is represented by one of the objects in the clusters. So in the k-means algorithm, a centroid has been created. Centroid could be one second. Okay. Yes, in the k-medides algorithm, so a new member will not be created. The existing data point will be represented cluster member. We will see. Okay. Okay. So we will see at the time of discussion of the k-medides algorithm. I can clearly show you what's the difference between the k-means and k. Now, how the k-means algorithm works. So given a k, because that's the drawback of this k-means algorithm is a, first you have to give what is the value, how many number of clusters you want to create. But we don't know that value, right? But assuming that I have provided the k value. So given a k, the k-means algorithm is implemented in the 4 steps. Like this. What I'm trying to do, the partition the objects into k non-empty subsets. Means the you have to partition your data set D into k non-empty subsets. And the computed seed points are the centroids of the clusters of the current partitioning. And initially, these seed points are initialized randomly. There is initially these seed points are, suppose there is initially these seed points are initialized. So if there is a point, there is a sample. Suppose there is a sample. There is a sample P. I don't know. This is a cluster C1. Suppose k is equal to 3. I don't know point P is belongs to the C1 or C2, C3. Because this point must belong to any one of this cluster, but I don't know whether the given point is belongs to the P1, C1 or C2. Or C2. How can I decide? So this point, you have to take the distance from the P2, C1 and P2, C2 and P2, C3. You have to take distance P2, C1, P2, C2 and P2, C3. Okay. So once I calculate the distance between the given point to the cluster centroid, C1, C2, C3, the closest distance, because I told the distance is a similarity measure, the distance is a similarity measure. 1 second. The distance is a similarity measure. So if this is the closest distance, it means that the least distance, it means that the point is very close to the cluster C1. Hence, I can say that the P is that belongs to the C1. So this is how the every point is assigned to one particular cluster. How we are assigning the cluster? So take the point and compute the distance between the given point to the all the respective clusters C1, C2, C3. How many clusters are CK? To which it is closer. So from there, so this is how the clusters have been assigned to the each and every data point. So when I'm doing so, initially these clusters seed points are random. So some members are here, okay, some members are here. But once it has some members has been assigned, so then there is a change in the cluster center. Okay? So now the members have been identified into that particular cluster. And when I compute the mean value of this cluster, so there is a change in this cluster centroid. So the cluster centroid maybe change from here to here. Suppose the cluster, assume that the cluster will change from here to here. So C1 dash. Then there is some points over here will come here. Some points over here will go from here. Means there is a movement in the shifting in the data. To say that there is the movement in the data objects. So that results into the new cluster centroid, and this process continued. Again, there's the mapping of the cluster data points to different new clusters and right. Now, one second. Okay. Right. So there's a change in the assignments in each object, and this leads to the different cluster. Like this process will be repeated for until there is a stabilization in the cluster centroid. Once there is no change in this cluster centroids, we can run this algorithm. So this is how the K-means algorithm wants to stop when the assignment does not change. Means when there is no assignment change in the members, then there is a stabilization in the cluster centroid. That's it. Right. Let's see with the help of this example how the K-means algorithm works. Suppose this is my given data set, and suppose a two-dimensional data. So I shown in the visual in the 2D plot. In the 2D plot, I have shown that how the two-dimensional data is look like in a given data set. And so I'm intended to create the two clusters. So so k is equal to I have chosen the k is equal to 2. And as I told you that arbitrarily the partition the objects into k groups. Initially what I'm so based on the seed points, so I will divide into, suppose assume that based on some seed point, so this has created as a one cluster. Assume that random. This is one cluster, and this is another cluster. Just assume. Okay. So now based on the initial seed points, based on that it is now the new members have been created. I can compute the mean of this group. The mean is here. And similarly, the mean of this, it is somewhere. Okay. So now I calculate two means. Now, as there is a mean, now I can reassign. Again, there is a reassign the objects. So in this process, what is happening here? We closely observe that this object earlier belongs to this cluster. Now it has come into new cluster. Earlier this was belongs to this particular cluster. Now it is converted into this cluster. So this is my new cluster objects. This is my new cluster objects. So with respect to these cluster members, again there is a change in the cluster centroid. So the cluster centroid from here, it has been changed to the here. The cluster centroid from here, it has been changed to here. Again, there is a change in the cluster members. New clusters have been formed. Again, we will recompute the mean. So like this, you have to repeat until there is no change in the cluster centroid or there is no movement in the cluster members. So when there is the cluster members are intact, when there is no movement in the cluster members, I can say that you can terminate the algorithm because the clusters have been formed. It doesn't make any sense even if you iterate any number of times even out because there is no change in the cluster centroid, and that does not lead to the any movement in the cluster members. Right. So let's see. I think the visualization of the K-means algorithm. I don't. Okay. Yes, are able to see this visualization?
Yes.
Yes, please watch. Okay.
This was being a collaborative effort of Ministry of Education and IIT Kanpur. It was collaboration and create this platform called SATI.
Just
What's the
can
main
you
purpose? They train of competitive exam. Just I'll
please
show
can
you
you mute
Sati's
yourself?
and she will be able to remember. See, these are the channels. Sati for engineering exams they give. For medical, channel number 2. For law,
Thank you. Let's see. So this is the final clusters, but initial clusters for somewhere here. I choose them. If you look at now, let's see. So these are my initial cluster. These are my initial clusters. So these are my initial clusters. Look at here. Now the clusters have been changed. So they change this. So once these cluster positions are stabilized, centroids have been stabilized, there is no movement in the cluster objects. So hence we can start neural web. Yes. One thing I want to make you note here is if you look at there is a one cluster, there is a one cluster with a single object. Can you observe? This is the object I am looking at. So this object is called an outlier. This object, because outliers are the different object which are significantly deviate from the other object. Because so this object is not similar to any one of these three classes. Otherwise, it would have been merged with any other. But this is so this kind of outlier. So we can detect the outliers. We can detect the outliers of the given cluster. Okay. This is an outlier. This is an example. Let's see the outlier. I can look at how the clusters have been shifting. Okay, so this is how the K-means algorithm works. So let us come back to the PPT. So if we looking at the some of the strengths, I can say the K-means algorithm. So is time complexity. The time complexity of this algorithm is order of n kt, where the n is the number of the objects and k is the number of clusters you are intended to create, and t is the number of iterations the algorithm will take to converge, means to minimize your error function or something. So it's a kind of optimization problem, but this problem, this algorithm may often terminate with the stucking at the local optimal solution, because it will not give the global best solution, but stuck at the local optimal solution. And this is as far as the optimization point of view is considered. So what are the other weaknesses if I'm considering algorithmic perspective is the applicable for only to the data objects which are in continuous in nature. So looking at for only continuous objects, like I mentioned earlier, income, so continuous approach. If I mention income as 70,000, 80,000, 90,000, or like that. So that is a continuous. If I am mentioning the income as a high, medium, low, it's a categorical attribute. For categorical attribute, we cannot compute the mean. Okay, so it means that if you want to compute the mean, your data set must be a continuous, right? So applicable only to the data which are data set which are in the continuous in nature. So, but if the data set is of categorical, so it's a category like yesterday I've shown one data set for the decision tree. So everywhere where the age is less than or equal 30, 31 to 40 and greater than 40. Three categories are income, low, medium, high. Three categories are student status, if I mention yes or no. Credit rating, fair or excellent. So if you're looking at all these attributes and category attributes, how can we run this K-means algorithm if it is a category data set? So there you can, instead of the calculating the mean, you can calculate the mode operation. You can identify the So that is called k-mode operation, slightly modified version of k-means to accommodate the, what I can say, the categorical values. In comparison, k-medians can be applied to the wide range of the data. So that's the reason there is the necessity of the developing the new versions of the k-means. That's called the k-medians. We will see just now. The need to specify the k means that you have to, in advance, you should know how many number of, what I can say, clusters are there inside. That is the delta, right? So finding of the k itself is the biggest problem. Okay, so that's another drawback I can consider. I can say it's very sensitive to the noisy. If the data, if any outlier is there, so that will impact the overall performance of the cluster. The cluster is going to form. So that's the reason. Why? Because we are calculating the distance. We are calculating the distance measure. What is the distance measure? We are using Euclidean distance. Okay. So because of that, it is very sensitive when I'm taking the Euclidean distance and up to the centroid to the outlier point, and when I'm squaring it to nullify the square root. So then this term, because the distance usually when I calculate the distance to the centroid to this outlier, because the outlier is far away from this cluster, so the distance is very huge. So this will impact the overall error value of your algorithm. That's the reason you can say the k-means algorithm is very sensitive to noise, but we can reduce this sensitivity by changing its, what I can say that the distance metric. Okay, instead of the Euclidean, you can use Manhattan. That's it. Okay? But not suitable to discover the cluster with a non-convex, because if the clusters is a convex in shape, so with that are detected by the k-means algorithm, if it's a non-convex like spherical or something like this, so then we cannot nested clusters or spherical clusters. Those clusters cannot be detected by the k-means. So this is as far as the shape of the clusters is concerned. So we cannot use it for the non-convex shape of the clusters. Right. Now, so what is the problem with the k-means method is the k-means algorithm is sensitive to the outliers. Means since an object with an extremely large value may substantially distort the distribution of the data. Of course, this will impact the overall. So what we can do that, so we can to reduce the impact of these outliers on the k-means algorithm, which is sensitive to the outlier. So they have developed this k-means algorithm. So what is the, instead of taking the mean value of the object, because it varies, so what we are considering the object in a cluster as a reference point. Because here we are not calculating any mean. Now, mean is not in the Mirides. K-Mirides algorithm, we will not calculate the any mean value. Instead, we can select the the data object as the midite, one of the data object, okay, which is the most centrally located object in a cluster. How we can calculate the midite? Sort it and find the mid value. That's it. How do you find the midite? So sort the value data objects and find the get the mid value. So that will be centrally located object of your cluster. Now let's see in this case. Initially we have two clusters. But in the if it is a k-means algorithm, so you might have created a new cluster, a new data object, over here. So this could be your C1 and this could be C2. This could be C1. Right. But this is in case of k-means algorithm. But when I'm referring to the k-medians, so we are selecting one of the data object as a k-median. We are selecting one of the data object because you will sort the data objects, identify the middle data object. So it means the centrally located object is not a new data sample which is created like C1 and C2 in the k-means. It is something like it will choose as one of the data object in your data objects. Okay. This is a slight modification if you so that we can reduce the impact for sensitivity towards the outliers. We can reduce by changing the way we calculate the centrally located object instead of taking the mean. So we are sorting the data objects with respect to certain value, finding its mid value. That will give the uh, centrally located object. Because so both the algorithms, the k-means or k-medians algorithm, it has a limitation of finding this k. It has a limitation of the k value. Then, because this k value we have to supply in advance, isn't it? the k value which is when they mentioned in the k means and k mean algorithm has to be supplied in advance. But how do you find this k value is a tricky, okay? So for that reason, in the literature, if you hear this in literature, there is a technique called elbow techniques, or you can say knee approach or elbow techniques. What it's saying that in the x-axis, I'm increasing the number of clusters, and the y-axis, I'm finding the total error is equal to summation of I is equal to 1 to k, summation of I in the p minus ci or something like this. So this is the error function. So you can calculate, you can say that where ci is the mean of the cluster. In case of k means, the ci is the middle object of the data set in a cluster objects, okay, middle point. That's how we will calculate the central terminus point. So when I know this, when I substitute the CIs, then you can take this one with respect to central object to all the rest of it, you will get the error. So this is called y-axis. And the y-axis, you will find the total error of the clusters, the total error of clusters. Right. Now what I'm trying to initially, when the k is equal to the number of clusters, so the error is high. The k is equal to 3, then error falls down. So like this, 10, right? So when the error falls down. So if you look at it, initially there is a sudden fall in the errors. At some point of time, there is no much fall. There is no much fall in the errors. There is like suppose something like this. Elbow. So what is this? So up to this, what is saying that up to this, there is a fall in the error. Means there is a huge reduction in the error. But here onwards, what I'm trying to say that there is no much change in the errors. Isn't it? No much change in the errors. Total error. So hence, so we are finding that region where there is no much change. So at this corner point, I can see the elbow point. This is called elbow point. So from here onwards, there is no much change. So this is my corner. So that is the optimal value of the k. So you can take into consideration, because even after when the k is equal to 4 here, so if I increase the k value, there is no much change in the error. So instead of that, so we can consider k is equal to 4 instead of 5, 6, because even if you take k is equal to 5, 6, there is no much change in the error. Suppose if there is error is something is 100, it is a 50, it is a 49. There is no much change here. But here in this region, there is a huge reduction in the error. So that's area where there is a steady, I can say there is no much change in the error. So that region is called elbow region, so that you can identify that. Means elbow region, the cornering point, again, the cornering point. Right. So this is how the what I can say that the k-mediated algorithm works. So initially they have taken the one of the objects. So this object is a centroid, and then they will rearrange these objects with respect to this. Then again there is a change in the new centroids. Okay, so this centroid has been changed to this, and so there is no change in this centroid. Okay? There is no change in this. Right. We will not discuss much on this. So if you're looking at what I mean that, so in the k-means algorithm, a new object has been created like this. But here, a new object will not be created. Existing data point is look as a central located object. So this is some comparison of the k-means and k-medians algorithm. Of course, k-medians algorithm is much better than k-means because it will handle the wide variety of the data. The less complexity and less sensitive to the outliers. The complexity in the k-means algorithm is the order of nkt, whereas the complexity of this is n minus 1, n minus k all square into I into k. So there's a complexity has been reduced. So more efficient and compared to less efficient. So, and this, it is very sensitive to the outliers, but it is not sensitive to the outliers because of the central terminus spans we have found by using the middle point by sorting all of the objects. So compared to the k-means is much better. Yes. So there are certain limitations in the k-means algorithm. As for the k-means and k-medians algorithm is considered, the limitation is the k value. The limitation is the how do we find this optimal k value? So there are other custom algorithms There are other clustering algorithms. Sorry. So there are some other clustering algorithms. So where you don't require these kind of inputs at all, where you don't require this kind of inputs at all. So let's see what are those algorithms. Those are called hierarchical based approaches and density based algorithms. We will see. Now let's spend the time on the hierarchical based, the time to see hierarchy. These hierarchical based clustering algorithms will choose the distance as a criteria for forming these clusters. Okay? So let's see how it is. This method does not require the number of clusters k as an input, but needs the termination condition. Why we require termination condition? Because so this termination condition is depending on how many number of clusters you want to, how many number of clusters you want to form. Based on that, the termination condition will be decided. Suppose if I'm talking the initially the each and every data sample is in a cluster initially sample. So the next cluster is being formed by merging two similar objects, by merging two similar. Then in the next step, I am merging the two other similar objects. In that case, I am merging the C and the DE. So first I am merging the DE, then I am merging the CD, then at the last I am merging A, B, C, D. It means that so we are starting with individual samples as a cluster. Now we are forming a single cluster. We're forming a single cluster. Okay. So this is called, we can do this in two ways. Well, if I'm going with the bottom up fashion, if I'm going with the, starting with the single object, single sample as a cluster and forming a single cluster, the whole data set will have a whole data set, forming the whole data set as a single cluster is called agglomerative approach. Means we are adding, every time we are adding new clusters. So, and because we are adding by using the some similarity measure by merging your similarity. Suppose if I the same process, if I see from the top down, so bottom up or just a top down. So if I'm seeing like this, then see there is called a divisive approach. Means we are starting with a single object and a single data set, a single cluster, and every step we are creating the new clusters. Means you are dividing your whole single clusters into multiple clusters based on the similarity function. So that's the idea. Okay. So based on the similarity, you are merging, and based on the similarity, you are dividing in the top down and bottom up approaches. This technique is called divisive approach, and algorithm which built on this idea is called Diana. And now, what is this? The dendrogram. So, what is this dendrogram in the hierarchy based technique? So, in the dendrogram is a visual representation of the how the partitions are being formed, or how the partition means how the partitions, not partition, the clusters have been merged, and how the clusters are created or divided. Okay? So this can be explained visually by this dendrogram. So let's see how the dendrogram is formed. Okay? Suppose this dendrogram, what it's saying that. So initially, I am merging objects E and F to create another cluster. And then in the next step, I am combining the two data points, two clusters to form the new cluster. And then, so this cluster is combined with the cluster D to create another cluster. And again, this cluster is combined with the C to create another cluster. And at the last, I'm combining these two clusters to create a single cluster. So this is as per dendrogram I'm saying. So this is the first, this is the second, and this is the third, and this is the fourth, and the last. Step one, step two, and like. So this is visually it mean by that. So which cluster has been formed first, and which cluster has been last, and which order it has been formed. But suppose what is the termination condition? Suppose I'm interested to create 3 clusters. I want to terminate my. So in that case, so you can we cut down this dendrogram such that at which level, at which level it has a 3 clusters. Suppose if I'm cutting down at this level, okay, I'm cutting down at this level. So this is one cluster, and this is another cluster, and this is another cluster, and this is another. So when I'm cutting down at this point of dendrogram, so I have a 4 clusters. Suppose if I'm cutting down at this upper level, suppose I'm cutting down at this level. In that case, what is going to happen? So this is one cluster, another cluster. So you can cut down your dendrogram at appropriate level. So depending on the how many number of clusters you want to create. So you are starting with n clusters and you are ending with this single cluster. So this dendrogram will say the how we are combining the clusters from the individual clusters. If I'm looking at the bottom of fashion, if I'm looking at the top to bottom, it will give a different uh, uh, view. Okay, how you are splitting your clusters. Right. The next is this and all is not required. Okay, so density based techniques. So the advantage of these hierarchical based technique is it can identify the clusters of any shape. If you look at, so this is the clusters of this shape circle, and this look at this is a triangle, this is a rhombus. So this is a clusters of full nested clusters. This, so it means what I mean that the complex cluster shapes can be identified with the help of the hierarchy. In that sense, it's much better than the K-means and K-means. So what is the other category of the clustering algorithms is the density-based techniques. So where everybody knows what is the density. In a given a range, how many people are staring, how many data objects are located on. So given a range, in a given a range, how many people are saying the population or something. So density, that is how we can measure the density. The specific metric for specific distance, how many people are saying the density and all. So let us see the idea of this density in the clustering analysis. So there are some algorithms which take this fundamental principle of density, definition of the density, and they created the clusters. Let's see what are those. The clustering based on the density is such as a density-based connection, the density connected points, because there's a one density point. This is another density region like this. So here, this is the density region, this is the density region, this is the density region. Again, this is the density region. I'm connecting all these the density regions, then it creates a cluster. So the major advantage of features is to discover the clusters of any shape, arbitrary shape, and it will handle the noises so that you can easily identify the outliers. And another biggest advantage is in a single scan, you can finish your trim, you can finish the clustering. You can form the clusters, you can form the cluster. You don't have to scan your data set multiple times. The need density parameters at the termination. Of course, as we are dealing with the density-based clustering techniques, we need a certain parameters that will define the what is the density, means like what is the radius, what is the minimum number of points, like we will see. Now, what are the density related parameters at the time of the algorithm, respective algorithm we are discussing, we can discuss. So what are the techniques which are follow this the density idea for forming the clusters in the DB scan? Very famous algorithm, it's called density based technique. It's a DB scan algorithm. So it was the first, it has been published in the KDD, one of the A-Star conference is called KDD conference. It's a knowledge data discovery conference. It's in the year 96 by the Easter and the co-authors. It has developed this algorithm and published their research work. There is a other variants of this the density weights called optics, the click algorithm. So this click has been developed by Indian researcher called Agarwal. Of course, he has published his work in the Sigmoid conference in the year 1998. So as I mentioned, what are the need or need to specify the density parameter? How do you define the density? To design the density, we have two parameters. These two parameters are called epsilon and minimum number of points. Means epsilon will talks about what radius you have to consider, for estimating the density. And how do next is minimum number of points is so the minimum number of points will give the what is the minimum number of points should consider the epsilon radius to be considered it as a density region. Okay, right. Now, what is this epsilon neighborhood? This n is called epsilon neighborhood of P. Means what is the n epsilon? This is called epsilon neighborhood of P. Means that so when the q belongs to the D, and so when I can say that q is belongs to D, so when I take any point q, and if I take the distance between the P and Q, the distance is the less than or equal to epsilon. Means there is a point P and this is epsilon. And if I draw a radius, I'm talking about a point Q. If the distance between these two is less than the epsilon, the distance between the P and Q is less than, I can say that. So this radius I'm calling as epsilon neighborhood of P. What is the epsilon neighborhood means? P as a center, P as a center, the P as a center, and epsilon as a radius. If you draw the circumferences, if the point Q lies inside this circumference, we can call it as the point Q is in the epsilon neighborhood of the P. This is the visual representation. Okay, this is mean by this. Now with this knowledge, so we have defined the epsilon. We also defined what is the minimum number of points. And with these two, I have defined the epsilon neighborhood of the point P. So point Q is in its epsilon neighborhood of the point P. The distance between the P and Q must be less than or equal to radius. It's an epsilon. That's what it means. Now, how can we use this definition for defining a two points which are directly density reachable? If there is a point P and there is a point Q, how can we say that the point Q is directly reachable from the P? So, to be a point Q is a density reachable from the point P, so it has to be satisfied these following conditions. What I am saying is, see, the point Q must be in the epsilon neighborhood like this, and the P, the point Q must be a 4 point. Sorry, point P must be a 4 point. What is the P belongs to the epsilon neighborhood of the Q. The P. Here I'm so this is reverse, okay. This is Q and this is P. As per this, okay. Otherwise, you can skip it and text. So this is now P and this is Q. What I'm saying that the P belongs to the epsilon neighborhood of the Q. The P is in this epsilon neighborhood of the Q, and this Q should be a 4 point. It should be a 4. Then I can say that. So as Q is a core point, what is the core point? If it is having the, so in its radius, when I make the Q as a center and the epsilon radius, if I draw the circumference, if I count the number of points here, if I count the number of points inside the circumference, it must be greater than or equal to the minimum number of points which are defined here. Right? Now let's see this example, okay? The minimum number of points I said 5 and the epsilon is equal to 1 centimeter. Okay, if I say, so this is the point Q, and this is the point Q. Now what I'm, if I draw the, this is a center and the epsilon radius. 1 second. If I draw This epsilon is a circumference, then this is the circumference. Okay. So when I draw this circumference with epsilon as a radius and q as a point, now if I'm looking at the p is on the circumference, it means that the distance of q is satisfied. Now the point p is in the epsilon neighborhood because it is on the circumference, no issue. And can you check if the q is a core point? How can you check the q is a core point? So in this, how many points are there? So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. There are 11 points are there in the neighborhood of the Q. In the neighborhood of the Q, there are 11 points. But how many points are there? Should be there to be eligible for the core point 5. So it means that Q is a core point. It means that the point Q is connected to a density region. So and that is the reason I can reach this point P directly. That's why it is called DDR, directly density reachable. The point P is directly density reachable. So this is the DDR, okay? This is the directly. This is the significance of the directly because it is in the neighborhood of the core point, in the neighborhood of the core point. Now, what is the directly the density reachable? Just now we are saying, what is the density reachable? So a point P is density reachable from a point Q. A point P is reachable from the Q with respect to the epsilon minimum number of points. If there is a chain of points, because here we have only one point, so we have a chain of points like P1, P2, like this. There is a Q. So there is a P. So there is a P. P1, P2, P3, and there is a Q. So if there is a chain of points, and if this chain of points, every point is a core point. With respect to these two, this is a core point. So when compared to these two, this is a core point. This should be directly density reachable. When compared to these two, so these 2 points should be DDR. When compared, this is a DDR like this. So there is a chain of points. There is a chain of points, and these points are satisfying the DDR condition. Direct relation means it means that from the point Q, and if you want to reach P, so there is a in between a region, a density region. The density region is there means when compared to this is a DDR. When compared to this, they should satisfy DDR condition. Indirectly, there is a density region between Q and P, so I can reach Q from a sequence of density region. That's why it's called density reachable, not directly, indirectly. Okay, we can reach. This is the density. We will see what is the purpose of this definition soon. Next slide. Don't get confused. Right. Now, what is the density connected points? What is the density connected points? A point P is a density connected to a point Q with respect to the epsilon minimum number of points. If there is a point O such that P and Q are density reachable from O with respect to the epsilon. Means here, so here a sequence of points are there. But in this case, the P and Q, there is no direct relationship. Means I cannot reach P and Q. But Y of O I can reach. Means with respect to the O, P, it is a density reachable, and with respect to O and I can Q, density reachable. So hence, the P I can reach Q via O. So this is called density connected. Means the P and Q are connected by a density regions and with respect to the O. Now, how can we use it? Okay, to define the density reachable, to define the density connected, we must know what is the density reachable. To define density reachable, you must know the DDR. So there are interconnections. Now, how can we use it? How can we use it in the clustering purpose? Now, let's see the idea of this. So, in the DB-scan algorithm, we'll use these following definitions to form the clusters. How it is going to use, let's see now. So the abbreviation of the DB-scan algorithm is the density-based spatial clustering of application with noise. So the beauty of this DB scan algorithm is it will identify the noisy points. Okay, so that's why it is called, the abbreviation of DB scan algorithm is called the density based spatial clustering of application with noise. Okay, even so, the DB scan algorithm will applicable if there is a data set which is having the outliers. Whereas in the k-means and k-means algorithm, they cannot detect the outliers, but they are sensitive to the outliers that will impact the overall cluster structure and overall number of clusters. But whereas in the DB scan, it is not the problem. It will detect the outliers. That's a beauty. So relies on a density-based notion of the cluster. A cluster, how we define the cluster? A cluster is defined as a maximal set of density connected points. How we are getting the density connected points? To find the density connected points, you must know what is the density reachable points. To find the density reachable points, you must know the directly density reachable points. Okay, so to find these density connected points and then form the cluster. That's it. Discover the clusters of arbitrary shape in spatial databases. Okay, because actually the intention was to it was first developed for the purpose of the spatial databases, but we can extend for other kind of data sets also. Now, so let us put in algorithmic form how this algorithm will be executed. So arbitrarily select a point P. So what we are going to do, that we are selecting a point P arbitrarily and retrieve all the points which are directly reachable, densely reachable from the point P with respect to the epsilon and minimum. What we are trying to do, we are trying to find out all the density reachable points. So once we are forming the density reachable, we are forming as a cluster. Okay. If P is a core point, a cluster is formed. Yes. If the P is a border point, means if it is not a core point, then it will be a border point. So no points are density reachable point. Then the DB scan algorithm will visit the another point of the database. So means if you select one point, it will traversing all the directions and to create the path. Suppose once it is finding a border point, so non-core point, then it will, because the border point will not create a cluster. So again, it is identifying another point to traverse in the to find the cluster. That is mean by the continue the process until all the points have been processed. So if I'm doing so, you can clearly observe that you can scan your database only once. So this particular figure will talks about the impact of those two hyperparameters. What are the hyperparameters I mentioned in the DB scan algorithm? The hyperparameters I mentioned in the DB scan algorithm. The hyperparameter which I mentioned in the DB scan algorithm was the epsilon and what is the epsilon? That's not what the radius and the minimum number of points. If you look at this particular, see in this case, then the minimum number of points have changed from 4 to you are kept the minimum number of points as 4, and I made epsilon as 0.5 to 0.4. So this is the epsilon is equal to 0.5, and I slightly changed from 0.5 to 0.4. Now let's see, there is a drastic change in the number of clusters. If you look at here, this is one cluster, this is another cluster, this is another cluster. But if you're looking at, we have so many clusters. So even what I mean that even if a small change in this epsilon will result into the multiple clusters. Similarly, in this case, now in this case, what I'm trying to do that, so I change the minimum number of points from 5 to the 3.5 and to the 3. So when I set the 3, minimum number of points is 5, this is one cluster have been formed. When I change to the 3.5, and this is there is a different number of clusters. When I change it to 3, so many clusters have been formed. So what I mean that you have to properly fine tune the hyperparameters of this DB scan algorithm, which are nothing but epsilon and the minimum points. Otherwise, it results into a different set of clusters. Okay. Right. There is another clustering algorithm, which is this. I think I will last algorithm, which I'm going to discuss because only 15 minutes are there. So I think I can try to finish it. So if you're looking at this, the clustering algorithm is called optics. It is called ordering of the points to identify the clustering structure. So this will works in similar lines like finding the distance and all. So it has been proposed, I think, developed by the people who has mentioned over Ankrest and Bruining and Trigale and Sander they published this work in the Sigmoid conference in the year 1999. So whereas the ZB-scan algorithm, the 1998, if I'm not wrong, you can check it. It's 98, this is 1996 sequence. They produce a special order of the database with respect to its density-based clustering. What we are trying to do that we are trying to find some interesting structure, cave structure. You can see, okay. Soon I will show you now. This cluster ordering contains info equivalent to the density-based clustering corresponding to the broad range of the parameters. So what we are trying to do that we are trying to estimate the some specific distance that is called what I mean that the reachable distance for each and every point. And if I'm arranging the points in the reachable distance according to the reachable distance of the points in the data set, so that points will create an interesting structure in the reachability matrix, reachability map. You will see. So good for the both automatic and iterative cluster analysis, including finding interesting clustering structure. Means this is very useful if you are finding the nested structures. If there is a nested clusters, if you're inside one cluster, another cluster, for those kind of things, it is useful. It can be represented graphically or using visualization technique. Let's see now how we can show it. Now, so to execute this algorithm, so we are coming up with an approach called the core distance. What is the core distance? Is minimum epsilon such that the point is a core. We have seen that the core means it should be eligible for minimum number of points. So what should be the minimum circumference, minimum radius I should consider to make it eligible a point as a core point? That is called the core distance, which minimum epsilon itself. So what is the reachability distance? So how can we reach a point from the core point? Okay, so if the point is uh, inside if the point is inside the epsilon, the core distance, then we are talking about the actual distance. Suppose the point is outside the core distance, we are considering the core distance outside the epsilon. Suppose the epsilon. So this is the point O, and this is the point P. So this is the point P. So if the point P is below epsilon, means in this circumferences, I'm considering the actual distance of D comma O. If the first point is somewhere here, so it means that then the core distance of the core distance means so that it should be in the circumference, so that it will be in the inside circumference. So that is called the core distance. So we have to consider the core distance. So which one is the maximum? Which one is the maximum? So core distance, so that is called reachability distance. How can we reach? If the point is inside that max I can reach within the epsilon. If the point is outside the epsilon, then the core distance I can reach that particular point. This is called reachable distance of a point P to the Q, P, O to the P. Okay. So with this, the core distance, or I can say reachable distance, how can we so if you what I'm trying to do that in the x-axis is my data points. And these data points are ordered in such a way that according to their core distances, according to their core distance for every data point, we are finding the core distance, So this map is called reachability map, and these are my data points. And if you're looking at, you are arranging in some specific certain order, so they will create an interesting structure like a cave. So this cave corresponds to this particular cluster, and this cave is created by this particular set of points. This cave have been created by this cluster. Means every cave, very nice, right? Is a cluster. By looking at this particular the reachable distance map, we can easily identify that. How many number of clusters have been there inside the data. How many number of clusters data. By looking at this, If I cut my reachability map at this point of time, I have only the three. If I cut at this level, this is one cluster, this is another cluster, this is another cluster, and this is another cluster. Okay. So the advantage of this, the optics is a density-based clustering is it will identify the nested cluster. If you look at cluster inside another cluster, cluster inside another cluster, so cluster inside another cluster. So if you look at it, if I'm considering this as a whole cluster, okay, this is a whole cluster, okay. So in this is a one cluster, and this is a nested cluster. This is a nested cluster. This is a nested. The whole, this is a whole cave is nothing but one cluster. Inside this we have sub caves, right? This will talk about the nested clusters. So the grid based is just like what we are trying to do that. We are split your data set into the grid cells, okay, like this. If we are talking about cells, the data points and cells, and you are applying the, what I'm trying to do, I'm applying the density of this. So number of points. If you see, accordingly, I can say in the cell, so 4, 17, 18.6 density. So you can set the threshold. If I set the threshold as a 5, I set the threshold as a 5, then so people, the cells which are above 5, the cells which are above 5, the cell threshold is 5, will be considered as a cluster, something like this. This is one cell, one cell, one cell, and all these cells whose number of points, so it will form a cluster. So form a cluster. So it will form a cluster, something like this. Something like this, it will form a cluster. These points will be ignored, okay? So just what is just an extension of the density based technique. So where we are the partition your data set into these cells, and for every cell you are estimating the density and this density, and these are the highly density cells we are connecting to form a cluster. So this is high level view. What is, how do you, it's called grid based technique, the grid based clustering. Okay. And there are so many other algorithms is also there. We have only few minutes are there, so we cannot discuss all these things. So if you have any queries regarding this, you can let me know. We have a 7 minutes are there for questions. We can discuss. K-means algorithm. Somebody has asked me how the K-means algorithm works again. So let me explain it again. Just yes. Suppose initially this is my seed points. This is my seed points. We have some cluster members. Okay. Cluster members. Initially it could be anywhere. Okay. So then I will assign. So what is the, which class it belongs to? How do you find? So for this point, I will take the distance from this, distance from this, and distance from this. For every sample has to find the distance from what is the closest cluster centroid. Means every sample has to find the distance from all this. Suppose I came to know this is the closest centroid, then C1 means this point is belongs to C1. So like this, every sample will be assigned as some class cluster label. So C1, C1. So this is C3. In the next iteration, so the C3 will be pushed into these clusters and form a new cluster. As because there is a shift, there is a movement in the data objects, there is a change in this cluster centroid. Because some objects are coming out, some objects will go out, that results in a change in the cluster centroid, and this process will repeat it until there is no change in this cluster. So it's a very easy algorithm. So yeah, Nityasri. So guys, have any questions?
Yes, sir. Uh, Yes, participants, do you have any doubts now?
No, sir.
Okay, thank you.
So, very
thank-
informative session, sir. So, I have a request, sir. Please share PPTs and videos of all these, sir, for future reference and study. So, also for assessment, also, sir.
Okay,
Sir
okay,
Jagat
sure.
sir, we definitely
So,
send these PPTs and videos to your mail after completion of all the sessions, sir.
yes, sir. But for the assessment, also we require the materials, sir, so that we can prepare, sir.
Yes, sir.
Excuse me, sir.
Yes, sir.
Am I audible?
Yes, sir.
Hello?
Yes, sir.
Yeah, sir. Please share the attendance of the last day and today.
Okay, sir. Okay, sir. I will share by today night or tomorrow morning, sir.
Okay. Thank you.
Okay, sir.
If no queries are there, I'm closing my session. Thank you. Bye.
Okay, sir. Thank you.
Thank you.
sir. Thanks a lot, sir.
Sir, wait for vote of thanks, sir, please.
Okay.
Good evening, everyone. It has been a truly insightful
thank you.
session today, and it is my privilege to extend our heartfelt gratitude to the esteemed speaker of this session, Dr. Ramalinga Swami sir, for his enlightening talk on the topic unsupervised learning. Sir, your in-depth explanation of cluster analysis, application of clustering, measuring the quality of the clustering algorithms, clustering approaches like partitioning. In partitioning, he explained about k-means clustering and strengths and weakness of the k-means methods, problems of the k-means method, and hierarchical approaches, density-based approaches, and grid-based approaches. These all are truly informative. Sir, your insights and knowledge have truly inspired and enlightened us. Thank you so much, sir, for spending your valuable time with us. Thank you once again, sir. Thank you.
Thank you, sir.
Thank you and good night. Bye.
Good night, sir. Bye.
Thank you, sir. Good night.
Tomorrow session will
Thank
start
you, everyone.
exactly at 6 p.m.